In this example, we'd like to try to find a power series representation of this function right here. Again, the main tool that we're going to want to use here is a geometric series. So let me just remind us, geometric series are of the form sum n goes from 0 to infinity, a sub naught or a naught to the times r to the power n. This always adds up to a0 over 1 minus r. Okay, I said always, I lied, right? It doesn't always add up to it. It adds up to this sum when what? What's true about r? You're screaming at me through YouTube, right? So it's when the length of r is less than 1. All right. So that, by the way, is going to be involved. This fact is going to be involved in finding our interval of convergence for this one. So what we would like to do for this function is try to represent this right-hand side as a sum that takes the form of the sum of a geometric series, and then we can just swap out, right, with this equal sign and kind of reverse our train of thought a little bit. So what we have to do is we have to start with this fraction, all right, and we have to try to get it so that we end up with a 1 minus something involving x on the bottom. So the radius doesn't have to be exactly x, but it has to be kind of like an x, right? And the main thing here when I say all this is that we need a 1, right? We need a 1 minus. So let's look at this. We have our 4 on top. We need to make a 1 plus or minus. Let's start with just plus, right? So what we have to do is we have to factor out this 3 from the entire denominator. And what we're left with is 2/3 x plus 1, right? And then that 3 shouldn't be downstairs anymore. It's got to be grouped with the a naught on top. So we end up with now 4/3 over, and I'm just going to switch the order here. This is still plus, right? Plus 2x over 3. I'll write it like this. And then the last step is we need this to be a minus sign, right? We need this to be a minus if we want this to be a sum of a geometric series. So we can do that. Remember, x is a variable, right? And so all these changes are affecting our interval of convergence. They're affecting the domain in some sense, but they're not affecting the fact that this is a sum of a geometric series. And so this can be written then as 1 minus negative 2x over 3. All right? And so this is just algebraic manipulation. These are equal to each other. We haven't done anything crazy here, right? But what we learn is that this term up here, this is our a naught of our geometric series, and this term, including the minus sign, this is our r. So the radius r of our geometric series is minus 2x over 3. Or you could say minus 2/3 x. Okay? Now, all we do now is plug this back in to our series. So what we learn is that f of x, our function, which is 4 over 2x plus 3, is equal to the sum of the geometric series, sum n goes from 0 to infinity, of a naught, that's our 4/3, right, times r to the power n. So that's negative 2x over 3, all to the power n. All right? And at this point, I mean, technically we're done, but we should always try to simplify this in practice. And what we can do is take out a negative 1 to the n, and then a 2 to the n, a 3 to the n from here, and this 3 to the n can get combined with this. So after all of this, let's look at what we have. We have our 4, but first I'm going to write the alternating part. So we have negative 1 to the power n. That minus sign is taken care of. Then we have our 4, okay? And then we have 2 to the power n, and then we have x to the n. That's everything on top. On the bottom, we have 3 times 3 to the n, right? And so we're almost done here. We can do some simplification. These combine can be written as 3 to the n plus 1, and these combine because 4 is actually 2 squared, right? And so this can be written as 2 to the power n plus 2. And our final answer here for this series in its most simplified form, or its nicest at least simplified form, is negative 1 to the n. 2 to the n plus 2 over 3 to the n plus 1, all times x to the n. And so there's our power series representation of this function f. Now, this is not it though, right? Because these functions are not equal for all values of x. Not even all values of x in the domain of f. Okay, the domains of these two are different. These functions are not equal. That's why we call this a representation, right? It's not equal to f, but it does not, at least not everywhere, but it does equal f on a certain domain, and that's where this fact comes in, right? So the interval of convergence is the domain of our power series. And recall that every geometric series converges when r is less than 1. The absolute value of r is less than 1. And for us, our r is this, right? So we just plug in negative 2/3 x should be less than 1. Absolute value takes care of the minus sign. And so we end up with 2/3 absolute value of x less than 1. And this tells us then that x should be, the absolute value of x should be less than 3/2. Okay? And so this is a symmetric interval around the origin, and our interval of convergence for this power series representation of this function is going to be negative 3/2 less than x less than 3/2. So that's the domain on which this given function obeys with the power series representation that we just found for it. All right, now look at these two values, right? So we're almost done here, but if you look at this value, negative 3/2 x, negative 3/2, sorry, when you plug that in for x, that's the value that makes this denominator become 0. And so that's a point that's not in the domain of f to begin with. Okay? And because of the way power series work, the intervals are always symmetric. They have to be, right? Geometrically, they have to be symmetric around the center point. The center point here is x0 equals 0. And so if you can only go 3/2 units to the left, that restricts how far you can go to the right. And we looked at this in the previous notes, but that's why the interval only goes to 3/2 in the right-hand direction as well as the left-hand direction.